Hello to all, welcome to the channel Money's Gate Tech Vision. In this lecture, I am going to solve GATE 2024 problems for the subject control systems. So for this lecture, I have taken electronics and communication gate paper. The topics which I have taken is common for electrical, electronics and instrumentation. So all those branch candidates can watch this video. Let me start solving the problem. First, I will read out the problem. In the feedback control system shown in the figure below, G of S is given, forward transfer function is given, and here R of S, Y of S, and E of S are the Laplace transforms of R of t, Y of t, and E of t respectively. If the input R of t is a unit step function, then what will be which one of the option is the correct one? So the options are given for error signal. Okay, steady state error. Steady state error. Options are given for steady state error. So we need to find the steady state error for the given system. Let me start solving the problem. So here G of S is given as 6 by S into S plus 1 to S plus 2. Okay, so the given block diagram is a negative feedback system. So we can write directly the transfer function as y of s by r of s, which is equal to g of s by 1 plus g of s h of s. So here the feedback is unity. So we can put h of s equal to 1. Now substituting the given g of s, 6 by s into s plus 1, s plus 2 by 1 plus 6 by s into s plus 1 into s plus 2. So after simplifying, this will become 6 by s into s plus 1, s plus 2 plus 6. So this is the transfer function we have found out from the given block diagram. Okay. So now the options are given for steady state error. ES is equal to, it is nothing but limit tends to infinity E of t, error signal. In S domain, we can write this as limit S tends to 0, S into E of S. So which is equal to limit S tends to 0, S into R of S by 1 plus G of S, H of S. So this is the formulation for steady state error. Now, observe the given options. Observe the given options. The given options are E of t equal to 0. And second option is limit tends to infinity, E of t equal to 1 by 3, E of t equal to 1 by 4. So A, B and C options are given as constants. See the option D, limit t tends to infinity, E of t does not exist. E of t is oscillatory negative. They have given for the not existing condition. E of t does not exist. So we have to consider the system, about the system. That is whether the system is stable or not, we need to find, because the options are given for the oscillatory signal also. So we need to find whether this given system is stable or not. So for that we can use the characteristic equation. We know this is the characteristic equation for the given system. Now the characteristic equation is, let me simplify the characteristic equation. S into s plus 1, s square plus s into s plus 2 plus 6, which is equal to s cube plus s square plus 2s square, that will become 3s square plus 2s plus 6 equal to 0. So this is the characteristic equation. So to find the stability, we can use Routh array. So I'm going to use Routh array for the s cube 1 and s coefficient is 2. And for s square 3, 6. S power 1, 3 into 2, 6, 6 minus 6, 0, 0 by 3 is 0. Okay. So now 0 appears in the first column. 0 appears in the first column. So we can take the auxiliary equation and we can find the roots. Now anyway, in the first column 0 appears means we can conclude that the system is not stable. system is not stable. Some roots are lying on the imaginary axis. Okay, or not, all the roots are not in left half of S plane. Some roots are lying on the imaginary axis. So we can say this is a marginally stable. This is a marginally stable system. So for marginally stable system or for unstable system, error signal will not exist. So limit t tends to infinity, E of t does not exist. E of t will be oscillatory only. So we can conclude with that the given option D is the correct one. Given option D is the correct one. See, 0 appears in the first column. So we can decide the system is not stable. Some roots are lying on the imaginary axis. So the limit t tends to infinity, error signal will not exist. It will be oscillatory negative only. So we can conclude with the option D. Let me move to the next problem. A satellite altitude control system as shown below has a plant with transfer function g of s equal to 1 by s square cascaded with the compensator. For compensator also one function is given where k and alpha are positive real constants. Now in the given system, the compensator system and 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 plant system is cascaded. So C of S is given for the compensated transfer function. G of S is given for the plant transfer function. So these two systems are cascaded in this. So first we should find out the gain for the cascading connection, and then we should find the closed loop system transfer function. Okay. So let me find the transfer function for the given block diagram. So this is Y of S by R of S, cascading connection of C of S and G of S. Gain should be multiplied by 1 plus C of S, G of S into H of S is 1. So we can remove that. H of S is 1. C of S, G of S by 1 plus C of S, G of S. Now substituting the value of C of S and G of S, it will become K into S plus alpha by S square into S plus 4 by 1 plus K into S plus alpha by S square into S plus 4. Now, simplifying this, K into S plus alpha by S square into S plus 4 plus K into S plus alpha. Okay, we know the denominator equation is the characteristic equation. We can find the characteristic equation from this. The characteristic equation is, let me simplify the denominator. This is s cube plus 4s square plus ks plus alpha k equal to 0. I am going to write this as first equation. I am going to take this as first equation. Why? We need to find the alpha. See here, see the question. In order for the closed loop system to have poles at -1 plus or minus j root 3, the value of alpha must be. Now, two poles are given for the system. -1 plus j root 3 is one pole. -1 minus j root 3 is another pole. Okay, we need to find the value of alpha. We need to find the value of alpha. So here we are having two constants. One is alpha, other one is k. We cannot find the alpha value without finding out the k value. So for that we need to form another equation. So now the characteristic equation can be expressed as a factors. I am taking since this is a third degree polynomial, we will be having three poles: P1, P2, and P3. So let me take the given poles as P1 and P2. I am going to take P1 as -1 plus j root 3 and P2 as -1 minus j root 3. Okay. Now I am going to write the characteristic equation as S minus P1 as three factors. S minus P1 into S minus P2 into S minus P3. I am going to substitute P1 and P2 in this equation. So S minus of whole is minus 1 plus J root 3 into S minus of minus 1 minus J root 3 into S minus P3 equal to 0. So multiplying this and this will become S square plus 2S plus 4 into S minus P3 equal to 0. Okay. Now multiplying this will become S cube plus 2S square plus 4S minus P3S square minus 2P3S minus 4P3 equal to 0. Now simplifying this, I'm going to write in this next slide. S cube, S square coefficients are 2 and minus P3. S cube plus 2 minus P3 S square plus, what are the coefficients of S? 4 and minus 2P3. 4 minus 2P3, yes. And then constant minus 4P3. Minus 4P3 equal to 0. So I am going to take this as second equation. Second equation. Now comparing first and second equation. Here I am writing again. The first equation we have found out from the characteristic equation as S cube plus 4S square plus KS plus alpha K. 4S square plus KS plus alpha K. So this is first equation. Now comparing 1 and 2. Comparing 1 and 2. What are S square coefficient? 4 and 2 minus P3. Equating this, we can find out P3 equal to minus 2. And then comparing the coefficients of S, K and 4 minus 2P3. So 4 minus 2P3 equal to K. Now substituting the P3 value as minus 2 into minus 2, that will become plus 4. So 4 plus 4, K equal to 8. So we have found out P3 value and K also. Now we can find out alpha easily. Now comparing the constant values, alpha K equal to 4 minus 4 P3. Now substituting P3 value as minus 2 and K value as 8. Alpha into 8 equal to minus 4 into minus 2, that will become 8. So alpha equal to 8 by 8, which is 1. Alpha equal to 1. So this is the answer. So we have found out the constant alpha, which is equal to 1. So option B is the correct one. Let me move to the next problem. Consider a unity negative feedback control system with forward path gain G of S is given. And here the impulse response, observe the question clearly. The impulse response of the closed loop system decays faster than e power minus t is. Okay. So impulse response, they have asked impulse response of the closed loop system decays faster than e power minus t. So for the response, which decays faster than e power minus t, what is the condition of k? That's what they asked. Okay. So first let me find the response. Response means first let me find the transfer function for the given system. Okay. So here y of s by r of s equal to g of s by this, since this is a negative feedback, negative unity feedback, so 1 plus g of s. Okay, now substituting the value of g of s, k by s plus 1, s plus 2, s plus 3. So k by s plus 1 into s plus 2, into s plus 3 by 1 plus k by s plus 1, s plus 2, s plus 3. So simplifying this, k by s plus 1 into s plus 2 into s plus 3 plus k. Okay. So this is the characteristic equation for the given system. Okay. So for what we have to find out, let me write the characteristic equation first. S plus 1 into s plus 2 into s plus 3 plus k equal to 0. Okay. Now read the question clearly. Impulse response of the closed loop system decays faster than e power minus t. So this transfer function is nothing but h of s. When you take the inverse Laplace transform, it will become h of t, that is the impulse response. Okay. Now, e power faster than e power minus t means, what is the Laplace transform of e power minus t? Laplace of e power minus t is equal to 1 by s plus 1. So, we are having one of the factors as s plus 1. Factors s plus 1. Now, what they are asking, normally, we will be drawing the s plane like this. Okay. Sigma will be the real axis and j omega will be the imaginary axis. Okay. So this is the real part of S and this is the real imaginary part of S plane. So normally this origin point is S equal to 0. So impulse response of the closed loop system decays faster than e power minus t. Okay, we have to find out the k value for which the response decays faster than e power minus t means 1 by s plus 1. That means s equal to minus 1. So instead of taking origin as the reference axis, we should take s equal to minus 1 as the reference axis. S equal to minus 1 should be taken as the reference axis. So we should find out, this is the S equal to minus 1. So we should find out the K value such that the impulse response decays left to S equal to minus 1. Okay, instead of taking origin as the reference axis, we are going to take S equal to minus 1 as the reference axis for the given problem. So for that, what I am going to do is S equal to minus 1 is the reference axis. That means S plus 1 equal to 0. S plus 1. Okay, S plus 1 equal to 0. So here S plus 1. So this S plus 1, I am going to change this as another variable. I am going to replace S plus 1 as m. I have taken another variable as m. Okay. Now, taking the characteristic equation, now s plus 1 can be replaced by the variable m. So, m into m plus 1 into m plus 2 plus k equal to 0. Okay. Let me simplify this equation. M square plus m into m plus 2 plus k equal to 0. So simplifying this, m cube plus m square plus 2m square, that will become 3m square plus 2m plus k equal to 0. So m cube plus 3m square plus 2m plus k equal to 0. So this is the characteristic equation for which s equal to minus 1 is taken as the reference axis. So we need to find the value of k for that condition only. So I have taken this equation as the characteristic equation. I am going to find the k value using Routh array. Okay. So taking the Routh array elements, the elements are, first row elements are 1 and 2. And for m square, the elements are 3 and k. M power 1, 3 into 2, 6, 6 minus k by 3. And m power 0, k. So k greater than 0. And then 6 minus k by 3 greater than 0, which is equal to k less than 6. So k is between 0 and 6. K is greater than 0, less than 6. So it may be from 1. it may be up to 5. Okay, so we can write this as we can write this as 1. So okay, here see the options. See the options. First option is k is between 1 and 5. Second option is -4 to -1. Not there. So option A is the correct one. It satisfies the k condition. Okay. So we have got this answer. Okay. K is less than 0. K is greater than 0 and less than 6. So we can conclude with the option A. Last problem. In the context of Bode magnitude plots, 40 dB per decade is the same as. So this is very easy problem. Actually, 20 dB per decade equal to 6 dB per decade. This is the equivalent. And this 6 dB plus octave per octave. Okay. So decade is the ratio for 10 times, and octave is the ratio for 2 times, doubling the frequencies. So we can conclude with that. So now given decibel is 40 dB per decade. So we can conclude 40 dB per decade equal to plus 12 dB per octave. So we can conclude with the A option. Option A is the correct one for the given problem. This is Mani's Gate Tech Vision. This is a channel for engineering lectures. You can subscribe to my channel. You can view the lecture series. And thank you very much for watching.